Today we're going to talk about direct variation. So what is direct variation? Let's start with an example to illustrate that. What is the relationship between distance and time? We've got Susan who can jog at a steady pace of 150 meters per minute for the first hour. So we're just going to assume she doesn't slow down, nothing happens, she doesn't have a red light, a traffic light to slow down. We're just going to assume a steady pace here. Create a table showing the distance that Susan jogs in 0 minutes, 1, 2, and so on up to 10 minutes. So we're going to create a table of values, which you might have previously called a T-chart, but we're calling them tables of values because we're putting values in the table. What should our table look like? So what are the two things that we are going to put in our table? Well, time is obviously one of them. This is going to be our time. What's the other value? It's distance. Meters is up here. So the question usually tells you what the two variables are. So here's the time. They wanted us to go from, the question asks us to go from 0 to 10 minutes. We're skipping a bunch because we're going to kind of get the hang of it. And now we need to fill in the distance. So when at 0 minutes, how far has she gone? At 0 minutes, if this is her steady pace, at 0 minutes, she hasn't gone anywhere. She's gone 0 meters. But at 1 minute, how far has she gone? When she has jogged for 1 minute, she's gone 150 meters. So then 2 minutes, 300 meters, because we're doubling what she had just done. She's doing 150 meters every minute. So every time she runs for another minute, she's done another 150 meters. So at 4 minutes, she's done 600 meters and so on. We have that pattern there. So we can skip down to 10. So this is important. Can you skip to 10, or do you need to keep adding 150, 150, 150, 150, 150? Or can you figure out how will I know how far she's jogged in 10 minutes without just adding a 50, adding a 50, adding a 50? Do you see the pattern? So it should be 1500. So what is the pattern here? Look at the relationship between these numbers and these numbers. What's between 1 and 150? What's the relationship? Between 2 and 300. Okay, so if you don't see it yet, I'll point it out in a minute. Identify the independent variable and the dependent variable. Remember, always, if time is one of your variables, then it's going to be the independent. So time is going to be my independent variable here. So I'll put that above here. This is independent, time, independent, and distance will be the dependent variable, which means if we were using x and y, independent would be our x, and the dependent is always our y, so distance would be our y. Now we have to graph the relationship. So we know along the x-axis along the bottom, we're going to put time. So I'm going to change that. Instead of an x, I'm going to use t for time. And I'll just put here that that's, well, actually, I'll write time. And we're measuring time in minutes. And the vertical axis is going to be distance in meters. So actually at the top, I'll put a D there, because that's our distance axis. And down on the bottom, that's T for time axis. We have to graph the relationship. So first of all, I have to think of a good scale to use. Let's look at our x values here on the chart. We have to go from 0 to 10. Do you think I can get 10 in here? Let's see, I think so. I'm only going to count every second. 1, 2, 4, 6. So I'm still counting by ones. I'm just not labeling them all because it gets really crowded. Now on the y-axis, my dependent, I've got to get up to 1500. So what am I going to count by here? Let's see. So let's just, we want to count by numbers that are easy to count with, right? I could count by tens, 10, 20, 30, 40, but that's not going to get me there. When these numbers are all increasing by the same amount as these are, they're all increasing by 150, then I can count by 150s. Students sometimes just want to take whatever numbers are here and just write them along the side. You can only do that if they're increasing by the same interval each time. So these y values are all increasing by 150 each time. All are the same. That means I can use that scale. but sometimes they're different, or they're they're uneven, and then I can't do that because my y-axis must increase evenly. So I want to count by 150s. My bottom one will be a 0. So this one right here would be 150. Okay, I'll write all these on. I won't skip this time, just because this is a little bit more challenging than counting by ones. So I'm going to count by 150, and I'm going to fill in every space. So there's my vertical axis, or dependent, or y. You can think of it as y. In this case, it's a d-axis, though, all filled in. So we're still on graph the relationship. We've got the independent variable down here, as it always has to be. Your independent is always x, and your dependent is always y. Now we're going to put these points on 0, 0. This is important. It's always really important to figure out if you're when your independent variable is 0, what's your 0? Your dependent variable is 0. It's not always 0, but this one is. So this means that before the time has started, she hasn't run anywhere. So I put a dot there on 0, 0, and then the next one will be 1 and 150, 2 and 300. Okay, and I'm expecting this to be a straight line because I noticed as I was filling in the chart that we were adding 150 each time. So that would be our first differences, right? Our first differences would be 150. So let me put the dots on the graph there. Okay, I've put all my dots on. So press pause and do that if you haven't done that yet, because you need to take the time to do it. Don't just skip right ahead. So look at how nice and linear they are. They're in a nice line. So now I'm going to get my ruler, which is always the hardest part for me with this tablet, and I'm going to try to connect the dots with a straight line. You should be able to draw a perfectly straight line here, okay? So I may not be able to, but you should be able to. Okay, again, I had a few stops and starts there, but yours is going to be straight. So I had to think about, am I going to extend it? I know I'm not going to extend my line here and put an arrow because this is 0. So she doesn't jog before that time starts. Does she continue jogging? It says she can jog for the first hour, so I would assume she's continuing to jog, but I don't know if her pace has changed. So I'm not going to really extend the line too much, but I have to put an arrow on here to show that, because it doesn't say she jogs, for an hour, reaches her destination. So she's continuing to jog. We assume we have to put an arrow on there. So there's our graph. Describe the shape of the graph. Where does it intersect the vertical axis? So this is really a critical part of today's lesson. Here's my vertical axis. Where does it cross it? So right here, sometimes we'll have a graph maybe that would start at 600 and then go like that. This one starts right at 0. The graph is linear. It intersects the vertical axis at y equals 0. And that's because when she had at time 0, there was 0 distance. That's why we have 0, 0. We have our graph passing through the origin here. Write an equation to find the distance in meters that Susan jogs in t minutes. So we're telling us the variables to use. We want to use d and t as opposed to x and y. We have to come up with an equation. So we've had a bit of practice with this, coming up with an equation. We go back to our question here. It's 150 meters per minute. So how do I get an equation out of that? It might be easier to look at my chart, 150 meters per minute. So look at the relationship between a number here on the left side, say 3, and a number on the right side. What's the relationship here? And I talked about this before. So what's the relationship between 1 and 150? What's the relationship between 2 and 300? It should be the same relationship, and it's going to come from this number right here. This is the relationship. So her distance is equal to 150 times her time. So she jogs for 3 minutes. We're just going to multiply that by 150, and we get this answer here, 450. So that's the equation that connects D and T. Part E says use the equation to determine the distance that she jogs in 40 minutes. So I don't have 40 minutes on my graph, and it would be way off here. I can't even extrapolate what that would be because it's off the graph. But I've got an equation. Use the equation. And hopefully some of you, by the time we were doing our table down here, you saw the pattern between 10 and 1500. So this is the pattern. So I have a new number, 40. Where does the 40 go? Does it go in for D or does it get subbed in for T? Well, it says right there minutes, so it's time. So it goes in for T. So I'm going to sub that in with brackets, always with brackets. 150 times 40, that's 6,000. So that means she can jog 6,000 meters or 6 kilometers in 4 minutes. So this whole example that we did here about Susan jogging was an example of our title for today, which is direct variation. So here's another example of direct variation. Do you see the connection between the x's and the y's? How do I get from a 1 to a 10? Is that the same thing I do to get from a 2 from a 20? The same math I'm going to have to process through to get from a 3 to a 30? Direct variation is a relationship between the two variables. In this case, we're going to have time and distance, in which one variable, this one, is a constant multiple of the other, meaning I'm constantly multiplying these numbers by the same thing to get here. I'm constantly multiplying by the same number, a constant, to get to this number here. That's what direct variation is. So if a line passes through 0, 0, it's an example of direct variation. That means I could have 0, 0 on this chart and it would still fit this pattern. So hopefully you've seen that the pattern is whatever my independent is, or my x or my time, I multiply it by 10 to get this number here. And that's the same with 0, 0. 0 times 10 is 0. The relationship between distance and time is an example of direct variation for this question. For example, the table shows the distances traveled in various time periods at a constant speed of 10 meters per second. So this one is whatever, it doesn't say if it's a person jogging, it doesn't say what it is, but it's 10 meters per second is this one here. So on your notes, you should be making a definition of direct variation. And these are good parts to have down here, especially the 0, 0 part. If your line passes through 0, 0, it's direct variation. That's how you can tell if you're just looking at a graph or just looking at a chart, a T-chart or a table of values. When time is multiplied by a specific number, in this case 10, distance is also multiplied by the same number. Another way to describe this direct variation is to say that distance varies directly with time. So our distance numbers, they're changing, right? 10, 20, 30, they're changing, they're varying. They're changing and it's directly related to the time number. They're not completely, they have nothing to do with this number here. They do. They directly depend on time. In direct variation, the ratio of corresponding values of the variables does not change. Right? In this case, it's 10 all the time. This is a 1 to 10 relationship, 1 to 10, 1 to 10. 3 to 30 is the same as 1 to 10, so the ratio is the same. So if D is distance and T is time, so what we can do is we can take any D value, like 30, divide it by the T value, 3, and you're going to get K. So K is that number, in this case it's a 10. K is called the constant of variation. So you don't have to worry too much about all of these little formulas. The constant of variation, what it means is whatever you're multiplying your X value by to get your Y value. That's your constant of variation. So what was the constant of variation in the example we just did with Susan's jogging distance? What was the number we were multiplying all of our x's by to get our y's? The number we were multiplying all our time by to get our distance? The constant of variation, K, was 150. For the last example. This is our last slide. Example 2. Stephanie earns $7.85 per hour working at a clothing store. So this is a really old example because that is not minimum wage anymore. Minimum wage is more like, well, it depends on how old you are, but it's over $10. Write an equation showing a direct variation relation relating time t and money earned e. So here's the variables we're going to use. So is it direct variation? Well, the question says it is, but how would you know? Basically, think about it. If Stephanie doesn't work, does she earn any money? No. So we've got 0, 0. 0 hours means 0 money. So it's direct variation. And we want to write an equation relating time and money earned. So you have to figure out what's independent and what's dependent. Because when we write equations, the equations are always in the form of, usually we have our dependent, we have our y equals, and then we have some number like that, and then our x after it. For direct variation, they're always going to look like that. But in this case, instead of y, well, instead, let's do the x first. This is independent, and remember the independent variable, if time is one of them, it's always going to be time. So time is going to be like our x, and money earned is going to be like our y. So our equation is E for earnings equals 7.5t. So make sure you write down that little kind of formula in the box here. That's always what it's going to look like. Earnings equals 7.85t. Next question. Make a table of values considering that she worked 12 hours in 1 week. So we've got a table looking like this. It's kind of small, and I'm not going to put in 0 all the way through 12. I'm going to skip a few, but I'm definitely going to start with 0 in time. What if she works 0, 1, 2, we'll do a 3, and then we'll skip and we'll go to 12. So if she works 0 hours, I already talked about this. If she works 0 hours, she gets 0 earnings, 0 money. What if she works 1 hour? If she works 1 hour, she's going to get, simply look up here, she gets $7.85 an hour, so she's only going to get $7.85. What if she works 2 hours? How are you going to figure that out? You're going to do 2 times 7.85 because she worked 2 hours. So you're going to do, I'll put it here in a different color. You're going to do 2 times 7.85. So that's going to be $15.70. Your calculator might just say a 7, but with money we have to have 2 decimal places, and some people might think that means 7 cents, but it's 70 cents. What about 3? So we're using this equation that we came up with here. We're looking for her earnings. Her earnings is 7.85, and right now my t value that I'm using is a 3. So I'm substituting into that, and then I will do 12. So press pause and finish the little chart here. So there's our chart. Now we need to graph the relationship. So there's a nice big graph for us. Then we have to think about what's going to go here. What's our independent? That's usually the easiest one to identify. So the independent one is going to be time. And again, usually in your textbook, if they give you a chart already set up, it's going to be the first thing in the chart. This is usually your x here. So this is my x, and this is my y. So when I look at my x-axis down here, or my time, I've got to go up to 12. Can I fit 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, just barely. So I can fit 12 on there. I'm going to label those, but I'm going to label every second one. There's my independent, my horizontal axis. My vertical axis is going to be earnings. So I'll put an E there. And what scale am I going to use? So here's a case where I don't want to just use these numbers and write them down, because those are not even numbers. Even though they're going up evenly, it's usually when we get to doing graphs, doing multiple graphs on multiple lines on one graph. If I pick really specific numbers like this, if I put 785 right here, and there's questions in your homework where you have to put 2 graphs on the same chart, and let's say your other graph has numbers like, 5, 10, 15, 20. They're going to be really hard to 20. They're going to be really hard to fit in if you use uneven values here. So for this one, you could do either. You could just put those numbers directly in, that these values right here. on the right, I'll get my pen back, you could just put these values right in because we are only doing one graph on this grid, but you always want to take a look at the question and see, am I doing multiple questions, because I don't want to mess up my axis. So we would often pick a number that if I would maybe count by tens if I wanted to just leave it open for other graphs. But because this one is increasing by 785 each time, I can go with the actual numbers that are there. But just to show you both, I'm going to count by tens here. So 10, actually I'm going to erase that and I'm going to label every second one instead of every one. So I've got my scale counting by tens, and now I'm going to put all of these points on. Remember, 0, 0 is an important one, so that's going to go right there. And I'm going to be kind of guessing because I chose a scale counting by tens here. So I'm going to have to guess where all these points go, like $23.55. Where's that? That's like maybe $23, maybe there, right? It's not going to be good, but I know it should be linear. So I'm just going to kind of approximate where to put my points on the grid, but they should end up in a roughly linear pattern. So I've got my first few dots on here, the first coordinates from here, because I only wrote in 0 to 3. Now I don't want to have to get out my calculator and figure out every 785 more, so I can fill in the dot. Because I know this is linear, because my relationship is linear, I can skip right to 12 and 94.20, and I can put that on. And I'm going to kind of keep my eye on these points here. I know that it should line up with them because I know I'm a little bit off, but I don't need to fill in all these dots that are in here, all these ordered pairs, because I know it's linear, and you really only need to, well, 2 points will make a straight line, but because we could make mistakes, we want more than 2. So I'm going to have a total of 5 points here, and that's good enough. So I think that's where my last plotted point will go, and now I'm going to get my ruler and I'm going to draw a line, and I'm going to put an arrow on the right end of the line because she can certainly work more than 12 hours, but I still have to put an arrow even though it looks like it's right at the edge of my grid. I still need to do that. So as usual, you're going to draw a perfect line, but I have a really hard time with my tablet, so you didn't need to extend it that far. And this should not be extended out here. That shouldn't be there at the bottom. So that's our line. I can label it with the title of the line, the equation, E equals 7.85t. That's the equation of the line. So that's part C, graph the relationship. Part D says extrapolate. That means we're going to take our best guess because we're going outside of the graph. Remember, extrapolate, extra, outside of the graph. Stephanie's earnings after 15 hours based on the graph. So 15 hours would be over here. What do you think? So we're just going to guess now. We're just going to guess where we think it would be. So when I take a look at this, well, I'm way off the graph, but that's what extrapolating is about. Extrapolating is about trying to just kind of guess based on the information you have what you think her earnings would be. So I'm going to say maybe at 15 hours, maybe like 100 and, I don't think it's 120, maybe it's like 115 or something. So I'm going to guess that at 15 hours, she'd be making about 115. So this is my guess based on my graph. But we have an equation, so we can of course figure it out exactly what she's making. This is our equation, E equals 7.85t. So where does the 15 go? Where am I going to substitute the 15? Is it going to go in for in for E or in for T? It's going to go in for T because it's time, it's hours, 15 hours. So we substitute that in and we get 117. So I was off, right? But I guessed 115 up here. So Stephanie earns $117.75 once she has worked 15 hours. And And there's the questions you need to do for your homework. You have to have graph paper. You must have graph paper. You cannot just write on regular lined paper or even blank unlined paper. You have to have graph paper. So all of your questions that you need to do on graph paper, and today's lesson is called direct variation because everything that we're talking about today, all of our examples are going through 0, 0, and they have a direct relationship between x and y.